Last time we talked about big O. We talked about what it means for a function to be big O of another function, and what it means for a function not to be big O of another function. And we noticed that big O has this connotation of less than or equal to. And it's a less than or equal to in a specific sense, right? In this sense that we are zooming way out and then squinting a little bit so that we can't read the numbers on the axes. But it's this sense that's formal and rigorous. And in some ways we can kind of carry that sense through in our intuition. Sometimes it's useful to be able to say less than or equal to, or greater than or equal to. And we use the Greek letter O for that. So the Greek letter Big Omega corresponds to greater than or equal to. All right, so I'm not going to write out the formal definition with all the words, but I will write it out in math just so that you can see the distinction to what it was before. So we say a function t of n is big omega of g of n, if and this is going to look very, very similar to before. So this means t of n is big omega of g of n, means that there exists a c and there exists an n such that some inequality holds for all little n's bigger than the big N. So formally this is there exists a c greater than 0, there exists an n, a big N greater than 0, such that t of n is greater than or equal to c times g of n for all little n greater than or equal to big N. Right, and so this is almost identical to the big O definition. What's the difference? The only difference is the direction of the inequality. Okay, so we can use a lot of the same intuitions that we have for big O and apply them to big omega, just to be able to to see what's going on. Okay, so let's think just a little bit about what big omega tells us. Okay, so let's say the following. Okay, so if some function, let's ask the following question. If t of n is big O of g of n, can we have the other way around as well? So can it be true? Can it be that t of n is also big omega of g of n? So here the answer is yes, and I'll give you one example that makes it true. But you know there are infinitely many examples. So the one simple example, the one concrete example I can give you that shows this is true is, so here the answer is yes, let's just be clear, is this. Let's let t of n equal n. And let's let g of n equal n. Okay, so it's clearly true that n is big O of n, and it's also true that n is big omega of n. Right? Why is n big omega of n? Well, let's figure out why this is true. Let's let c equal n equal 1. Then what do we have? Well, we have n is greater than or equal to c times n for all n greater than, in fact, always, but for all n greater than 1. Okay, and this is just true because c equals 1. So we have n is greater than or equal to n. Okay, so now this is something that you may not be used to seeing. It may perplex you at first to see something greater than or equal to itself, but of course the key is in the or equals part of the greater than or equal to, right? So n is greater than or equal to itself, specifically because it is equal to itself, right? All right, so what if we have the following? Let's think about this. If t of n is big O of g of n, then what if we swap them, right? What if instead of switching the omega, what if we switch the g and the t as well? is this true? Is g of n big omega of t of n? Right? So take a minute, think about this, pause the video, think about this, and then come back and see what the answer is. All right, so what do we have here? Well, if t of n is big O of g of n, what does this mean? This means there exists a c greater than 0, there exists an n greater than 0, such that t of n is less than or equal to c times g of n. Right? Now, what does this mean? And specifically for all little n greater than or equal to big N. Okay. So now what does this second statement mean? So what do we need to show that this second statement is true? This says there exists a c, and I'm going to call this c prime because it might be a different c than what we saw before. There exists a c prime greater than 0. There exists an n prime greater than 0, such that g of n is greater than or equal to c prime times t of n for all n greater than or equal to n. Okay, to n prime specifically. All right, so now let's do this. So let's pick some numbers. So let's actually pin down some of these and then chase it down and see if we can show this is true. So first, what I want to draw your attention to is the fact that we've got this inequality here with g on the big side of the inequality. And then we've got this inequality here with g on the big side of the inequality. So all we have to do to show that this is true is figure out a way to manipulate our c's so that we can show that the second statement is always true whenever the first statement is true. Okay, so let's do the following. Let's let n prime just equal n, right? So we've got that. And then let's let c prime equal 1 over c. C prime equal 1 over c, right? So if c is a very large number, then maybe what that means is that I have to scale g way up to make this inequality true. And so if c is a very large number, then c prime is going to be a very small number. And so scaling t way down to make this inequality true is going to be equivalent to scaling g up in the other inequality to make the other inequality true. So now let's just plug stuff together and see what we have. So we know this is true, so we know for all n greater than n, which equals n prime, we have that, let me make sure this is in my screen so I can read it. We have t of n less than or equal to c g of n. All right, so now we can just work with this. Let me keep the c prime definition in here. So if c prime is equal to 1 over c, then that means that c is equal to 1 over c prime. Okay, so what do we have? Well, we've got 1 over c prime times g of n. And now this piece, we can just move that c prime over to the left, and we get c prime times t of n is less than or equal to g of n. And that's the inequality we wanted, right? I'll circle it in orange, right? This inequality is exactly the same as this inequality, right? So what's the consequence? Well, the consequence is just this. This is true, right? If t of n is big O of g, then necessarily g must be big omega of t. Right? So this is yet another way that the intuition that we have about greater than or equal to and less than or equal to with big O and big omega kind of goes through and works well.